Okay, our second presenter is Tom Dillinger. He's, in addition to being the author of the latest TEC's VLSI design methodology, he's been in the industry for over 30 years, involved in circuit design, fabrication process research, and EDA tool development. And he's been responsible for design methodology for ASICs, SoCs, and microprocessors for IBM Sun and AMD. So we'll turn it over to Tom.
Thank you, Ira, very much. Now, my understanding is that Ira is going to be providing the slides later, so this is going to be a little rude of me, but I'm going to skip the introductory part of the slide set. You can look at that later. The first couple of sections really relate to challenges that designers encountered as we've moved forward through various silicon process generations, FinFETs and multi-patterning technologies. So the first few sections really are changes in design styles that frankly have been addressed and for the most part solved. That won't be as much fun as talking about what challenges are we facing today. The people that are able to solve the future challenges that we're going to talk about are going to be able to reap some rewards from that. So we are going to, and again, this is rude, I know, but these are all in the slide set that Ira will be making available. And here we go. Whoops. So we're going to have a little fun. I tried to create what I thought, very subjectively, are the top 10 challenges that we're facing right now. What are the headwinds toward leveraging some of the advanced silicon and packaging technologies that are available? So with apologies to David Letterman, everybody here remembers David Letterman, right? Top 10 list. Okay, we're going to have some fun. Number 10, you may be aware that the only real trusted foundry for the United States government has recently declared they're done at the 14 nanometer, 12 nanometer node. That's probably okay for today's DoD electronics, but the United States government is struggling with what is their future roadmap to get trusted electronics. So they are providing a great deal of research contracts and funding to individuals to go look at what they're calling split manufacturing. How can I leverage the advanced silicon technologies that are available overseas, Taiwan, Korea, and yet bring the balance of the design back to the United States to a foundry that may be able to complete the back end of the line metal processing where the lithography requirements aren't as stringent. So the picture on the bottom kind of is intended to indicate sort of the concept where I still do a design layout, but I have to now separate the front end of the line that I'm going to send overseas to a non-trusted foundry from the back end of the line connectivity that I am going to complete here domestically. Why is this an issue? Well, if I'm sending a critical, mission-critical design overseas to a non-trusted foundry, A, I want to make sure that they aren't able to reverse engineer it. B, I want to make sure that there is not any latent Trojans or pick your favorite term for something that does not belong in the design that was added maliciously that then could affect the performance of the design once it's completed and shipped and out in the field. People are researching, how do I design so that I can accommodate this split manufacturing between a non-trusted and a trusted foundry? Challenging problem. Number 9, we are dealing now with new device types, or will be very shortly, new device types and new device structures on our chip designs that we haven't seen before. I think Anand may have mentioned MRAM, magneto-resistive memory cells, offer great promise, but that's a totally different set of materials and circuit design styles and integration technology than we have dealt with before. So how am I going to make sure that I have the appropriate test and qualification and failure analysis strategies for some of these new structures? Particularly if I'm looking to put some of these new structures in a high reliability application, I want to make sure my qualification strategies will cover the failure mechanisms of some of these new materials. And this is all brand new. The foundries are saying MRAM will be available, but personally I have not seen kind of the balance of the industry saying, and we know how to test, analyze, do FA, do diagnostics on these new materials. Number 8, this one's a little bit more esoteric. I remember when I went through school, electromagnetics was not my favorite subject. But let's face it, electromagnetics is more and more important for chip and package designers. Package designers and board designers, they've dealt with inductive modeling of traces for high-speed interfaces and high-speed signal communications for some time. Chip designers have not really had to deal with that to a great extent. At today's data rates, we will definitely be looking for help in extracting R, L inductance, C, and mutual inductance models, particularly for very high-speed signal communications. The picture at the bottom is from NVIDIA, who said, we're having trouble. We're generating very, very high-speed clocks on chip, and we're seeing jitter beyond our design margins. So the yellow curve is, let me see if I can do this here. The yellow curve was the jitter that they had expected based upon just extracting resistance and capacitance from their layout. The red curve, and I know you can't see the scale here, but when you get the slides you can magnify this picture. The red scale is the jitter that they modeled and simulated on their very high-speed clocks on chip with resistance, capacitance, inductance, and mutual inductance being extracted for the clocking network that they were using to send very high-speed signals. So the concept now of I need to extract L and mutual inductance between critical signals is going to be a big challenge, right? A lot of us chip designers slept through our electromagnetics classes. We're going to have to dust all that off to learn more about modeling and simulating inductance and mutual inductance. Okay? Number 7, everybody here I'm sure has heard of, we're all going to be driving class 5, self-driving autonomous vehicles in the not too distant future. Well, class 5 automotive electronics requires some sort of fail-safe operation, right? If I'm on the road and something fails, I want to make sure I can fail over if it's non-critical, or fail safe, continue to operate successfully if it is a critical part of that autonomous vehicle. How do people do fail-safe designs today? Well, the people that can afford it do something called triple modular redundancy. Basically, the military does all the time. I build 3 of a critical unit, and then I have a voting circuit that basically says, well, if one fails, the 2 majority systems will still result in correct operation and continuing operation, not a failure. Well, the Department of Defense has indeed, the Department of Defense has indeed defined how do I insert voting circuitry and make sure that I've inserted that voting circuitry correctly. That's a solved problem. But what's not a solved problem, in my subjective opinion, are 2 things. Number 1, I can't afford an autonomous vehicle that costs as much as a Department of Defense contract vehicle. So how do I do fail-safe operation economically? I'm not sure we know how to do that yet. What are the critical systems in an autonomous vehicle that really do require fail-safe, or even for that matter, fail-over operation, but fail-safe specifically? And then how do I do voting logic that I can trust? Because there is still an awful lot of research underway. What if there is a manufacturing failure in the voting logic? What if there's a fault in the voting logic? Well, when I test the silicon, the two working subsystems, they'll still work. So there is an awful lot of research. How do I design voting circuitry that can accommodate a typical silicon manufacturing defect? Still an open problem. Lots of progress on it, but trust me, or at least I'm not going to be driving an autonomous vehicle, the first one that comes off the manufacturing line. I can tell you that for sure. Number 6, okay? All of you are familiar, I'm sure, with the terms infant fails, HTOL qualification, bathtub failure rate curves, wear out region, all that kind of stuff. Again, we're going to be dealing very shortly with lots of new device types and materials that I'm not sure we know exactly how do I burn in and screen and define infant fails so that all I'm shipping is good product with a low failure rate. It's kind of related to the one we talked about earlier with new materials and FA, but before you get to FA, I have to decide how am I going to burn in and screen these parts. So the picture on the right is particularly interesting because some of the new materials that are being discussed, for example, for underfill, so the material that encapsulates the die in the package, have some very unique strength and coefficient of thermal expansion characteristics. You would like the strength, the brittleness of the material to go down as temperature increases so that it can accommodate differences between the silicon and the package, right? Kind of not as brittle, but more flexible. The problem is that these cool materials that have a strength that becomes less brittle as temperature goes up, their coefficient of thermal expansion goes up as temperature goes up. So all of a sudden they're reintroducing the stresses between die and package that we were trying to eliminate by having this cool material who wasn't as brittle at high temperatures. So how are we going to do burn-in and reliability testing at some of these advanced nodes with these new structures and device types? Big challenge. Number 5, kind of related, a little bit different. This one is my favorite question to pose to anyone. Today, when you do a fit rate calculation, you are assuming that all of the failure mechanisms are independent. Basically, I calculate a fit rate for that failure mechanism. I multiply it by how many metal wires, vias, contacts, whatever that structure is that's replicated across the die, and I sum all those up, and that's my fit rate. Is that still really accurate? I mean, does it make sense to say that the failure rate of a metal connection on a 5 nanometer die, which is effectively infinitesimally small, but as Anand said, I'm potentially putting billions and billions of those structures on a die. Is it still mathematically correct to say that I can take an infinitesimally small failure rate and multiply it by billions and come up with a realistic fit number? I'm not sure we know that, right? Are our failure mechanism models still the right method to calculate fit rates? And in particular, as we said, there's going to be new materials, these MRAM structures specifically, that I'm not sure we know exactly what to use for fit rates for these. A related topic, still on number 5, is devices age with time. The methodologies to accommodate aging as a product is out in the field are still a little soft, to be very honest. And in particular, if we're talking about automated class 5 vehicles, autonomous driving, we are talking about 20 years out in the field, not just a few years. I'm not sure that we've got the methodologies that can accommodate how do your subsystems age over a 20-year period, particularly in an automotive class environment. And what does that mean in terms of the design margins that I need to include at the very start? Still a methodology that's kind of in flux, to be honest. This one should not be a surprise to anyone in here. We are to the point where we cannot design electronics, but what we have to include thermal and mechanical structural analysis at the very beginning. The temperature extremes are, as Anand mentioned, are getting greater. We have applications that are much, much more demanding in terms of their thermal and mechanical requirements than we've ever had before. One of my favorites is here on the bottom right. You can't turn on the TV, but what 5G is coming, right? T-Mobile, AT&T, Verizon, they all say, my 5G network electronics is ready to go out and buy your 5G smartphone. I'm not sure that that's really the case, because 5G transmission and reception requires very elaborate radiation patterns. Do we know how those patterns, how that electronics behaves when it's on a pole or on a building that is in northern Minnesota or Phoenix, Arizona, and subject to the kinds of external thermal conditions that that environment may provide? So electrical, thermal, and mechanical analysis moving much earlier into the design cycle. No longer can we just design a chip and throw it over the wall to the packaging and board design engineers. Okay. Every chip system designer, project manager, program manager will tell you the #1 resource investment in any project is verification, functional verification. I have to write a model of the system that I'm envisioning, and I have to simulate it as thoroughly and as comprehensively as I can. Problem is that thanks to our foundries and thanks to the packaging technology engineers, I can accommodate, and Anand showed the huge Cerebrus design, I can accommodate much more functionality in kind of a single subsystem than I ever could before, which is putting huge stresses on how do I model that, how do I simulate it, how do I get that design ready to send to fabrication. Well, for quite some time, the EDA industry has said, well, we'll just make designing easier and easier and easier because we'll just raise the level of model abstraction that you use to describe and capture your model. Rather than writing, I'm old enough that I used to draw schematics and logic gates and build complex functions from schematics. Well, then we went to something we call hardware description languages, Verilog, VHDL. And the EDA industry is saying that's out of gas. I just cannot simulate that model quickly enough and thoroughly enough so that I can meet your project schedules. So the EDA industry is trying to encourage designers, move up. Start coding your functionality in a different, more abstract language, and we'll try to verify it and simulate it more quickly to allow you to get all of the test cases, exercise that you need to exercise. So designers are off writing MATLAB. Some designers are off writing C. The AI companies that Anand mentioned, they're off writing something even more bizarre called TensorFlow. And so EDA vendors are trying to provide simulation and verification support for a wide variety of modeling languages and types. And they're doing a good job. I mean, don't get me wrong, I can write TensorFlow and simulate a neural network. I can write MATLAB and simulate some digital signal processing function. But now I'm counting on the EDA vendor to take that higher level description and synthesize it down to circuits, something I can actually functionally build on an IC. There is a huge layer of trust associated with how do I take that high-level description that simulates more quickly and trust that Yep, the synthesized result, the actual circuits that the EDA vendor tool provided me, is indeed a fully accurate, comprehensive representation of that higher level model that I simulated. There's research underway. How do I prove that those two representations are truly 100% functionally equivalent? That's a big challenge. It's inhibiting, really, designers just jumping on the bandwagon for some of these higher level model representations. Okay? The other issue with trying to move up the model representation and abstraction curve is the whole reason that an architect might write something at that high level is to simulate it, run more test cases through it, verify it as thoroughly as possible. But anytime you try to write something more abstract, you're going to lose something. Something falls through the cracks. How do I provide power to all of these subsystems? What if I want some of these subsystems to go to sleep periodically and I want to gate the power? What if I have very specific performance requirements for one of these subsystems? Well, the EDA industry has said, well, we'll write a whole boatload of side files. Something called a UPF file describes my power intent for the design once it gets from an abstract level down to the synthesis and subsequently the chip physical design step. So now I'm counting on the EDA vendor to take a high-level representation, MATLAB, C programming language, synthesize it, but also read in my side file that has all of the detail that I didn't want the system architect to have to describe when they were writing their MATLAB or their C, and now they have to merge both of those representations into actually the circuits that I can build. And how do I prove that this side file is also 100% accurate and correctly reflected in the resulting models that come out of the synthesis and the chip place and route flow so that the final design is 100% equivalent to what both the system architect described as well as me, the chip designer that had to worry about power and clocking and voltages and the details that are not in that abstracted model. It has to be accurate. Big problem for the EDA individuals. One other problem for the EDA individuals is everybody here, I'm sure, has heard the term. It makes me shudder because I've had to deal with them as well. Everybody here has heard the term engineering change, right? What if the program manager comes in at the 11th hour and says, whoops, I need a feature that you have to embed in order to be market competitive? I've already gone through, the system architect, he's long gone, right? He's at another company or he's on another project. His abstract model's done. And I've gone through all of these steps from his abstract model and my detail down to something that I'm about ready to tape out, and an engineering change comes in. Wow. Okay, I'm pretty good probably at adding a few logic gates here or ripping up and rerouting some wires to embed a small engineering change. But what do I do about that abstract model? How do I make sure that it's accurately reflected back up to that abstract model so that I still have a 100% valid, accurate representation? We don't know how to do that. Okay? The engineering change flow from detail back to models of higher and higher abstraction, big, big challenge. EDA industry is working on it. They are trying to improve their equivalency capabilities. First EDA company that is able to say, I can prove high-level abstraction is truly 100% functionally equivalent to what you are taping out, they're going to make some money. Number two, I'm sure many of you have heard the term digital twin. Basically, the EDA industry is turning to the automotive industry, and this is, I think, mostly being applied relative to automotive design. The EDA industry is turning to the automotive industry saying, give me models. Give me models of sensors, right? give me models of cameras and LiDAR and radar and all of the sensors that you see on the Google car that drives around. And give me models of the actuators that you're planning on using so that I can take sensor input, effectively digital sensor input. So somebody's doing the analog to digital conversion in your model. Give me models of your sensors. I'll build the controllers and the electronics, and then give me models of the actuators so that I can prove that I'm sending the right signals out to the actuators that will invoke the braking system or the steering system. So the EDA industry is leaning on the automotive industry for models. The EDA industry is building these very, very large simulation engines that assume a digital model, so the digital twin, and attempting to simulate effectively a full automotive system. They're making good progress. They really are. There's companies out there that are saying, I'll even generate thousands and thousands of the corresponding scenarios that are effectively to prove that your autonomous vehicle behaves correctly in the face of some incident or some case that I have to prove is correct. So we're making good progress. Okay? The problem is, how do you trust those models, right? It comes back to trust. How do I trust that Bosch sent me a correct model for their sensor? And how much do I have to simulate? There's a quote going out, I believe it, I hadn't thought about it much, but somebody actually said, to ship a Class 5 autonomous vehicle, you're going to have to drive 8 billion miles. Clearly, nobody's going to do that. And in particular, you're not going to present all of the risk scenarios to somebody on the road. I mean, I'm not going to volunteer to be the pedestrian that jumps in front of a car while you're testing an autonomous vehicle, trust me. So you are going to have to simulate and verify it and trust these models and use these large simulation engines to prove that all of the scenarios that you can think of are working correctly. All right? Big challenge, trust, when it comes to autonomous vehicles. Because, and here is the bottom line, who is going to authorize, what government agency is going to say, you have adequately done sufficient simulation on your digital twin model and field road testing to get a regulatory agency of our federal government to say that's a valid Class 5 vehicle? I'm not sure any regulatory agency is stepping up to that challenge. Who is going to authorize, you've done enough simulations, you've done enough road testing, and your models are all correct to get the Class 5 USDA seal of approval? One of my favorite quotes is here at the bottom. Nice ringtone. Again, a lot of trust is going into these digital twin models. One of my favorite quotes. All models are wrong, but some are useful. Who is going to step up to the challenge to say we know how to do verification of a Class 5 automotive system? Okay? And finally, number one. I know you're all waiting for number one. The packaging technology people in this room have done an exceptional job. The silicon people are doing an exceptional job. There is a wealth of development underway and under, I'll call the field, heterogeneous packaging or heterogeneous integration. Some people call it chiplet integration. I don't like that term. Basically, today we can stack 3D structures where a base chip is thermal compression bonded to chips, one or more chips, directly face-to-face or face-to-back if you have through silicon vias. In the future, they're envisioning even going further, thinning the chips that are today thermocompression bonded to the base and allowing multiple 3D layers of chips to be stacked, thermocompression bonded, and packaged. That's cool. I have no doubt that the packaging technology people will achieve that. The problem is, go to your system architect and say, okay, how are you going to partition your system design that is optimum given all of these variables, all of these degrees of freedom to choose from? How are you going to make sure it's power efficient, performance efficient, cost efficient, and meets all of the reliability, system, and security and safety goals we were talking about for some of these high-rel applications? We don't know how to do this level of system definition and partitioning to meet all of those optimizations yet. Some people call it pathfinding. If you do a Google search on EDA vendors and pathfinding, you'll see some people saying, yep, we're working on pathfinding to allow system architects to be able to come up with optimum solutions for a very heterogeneous kind of package. We don't know how to do that yet. So I'm going to leave you with, this is the acronym to remember. We have to figure out as early in the design process as possible, not only how to achieve power, performance, and area optimizations, but with these advanced packages and chip technologies, how to meet cost, reliability. We talked a little bit about security, right? Failover and fail-safe kinds of electronics designs. I have to meet security requirements, and I have to meet safety requirements. What happens if it fails? How do I know that my system responds correctly? So for those of you that are used to throwing around the acronym PPA, I'm going to propose a new acronym, PPACRSS. Or if you're a football fan, it kind of sounds like Packers that play the 49ers in 2 weeks. Power, performance, area, cost, reliability, security, and safety optimizations, given the potential for very, very advanced packaging and silicon design, huge #1 challenge. Whoever solves that's going to make a lot of money. Thank you very much.